ML is not magic. It's not the answer to life's problems. I hope somebody will ask me at some point whether ML or AI is going to take over the universe and make humans obsolete, because I've got an answer. I've been thinking about it for a long time. It relies on hours or even days or weeks of training. The models I build take 6 to 12 hours to train. Some of my colleagues in the university have got models which take weeks to train. I know because we have to fight for the servers. We are heavily compute intensive for training, but much so for the evaluation and prediction and classification. So when you're doing the training, you're using oodles of processing power, but more GPU power. We'll come into the reason why we use GPUs in a minute. But when you actually do what we call the evaluation, so then you put in the unseen data through and you're using it in a real environment, the amount of process and compute power you need is significantly reduced. So as an example for the stuff I'm doing, I got 4 GPUs, RTX 5090s or something. I don't know if anybody knows about GPUs. They're super powerful GPUs with 16 gigs of memory on each one. And it'll take 6 hours to train my data set. But to do the evaluation, the actual proper application, I can run it on a Jetson, NVIDIA Jetson. So that's the comparison. So some applications, IP network optimization, we can use ML for network congestion detection, long flow TCP and ARQ detection, elephant flow and mice flow detection, and security intrusion detection as well. This is a big thing coming down ML, and there's a lot of research going on into sort of detection of people doing things they shouldn't. You often hear of comparisons to the human brain with ML, and there's sort of good reason for it, because the brain is a biological interconnect of billions of neurons, and this is at a very simple, high superficial level. As humans learn, the interconnects are added, removed, or updated. That's how we learn. Take a baby, that's an apple, that's an apple, that's an apple. Do it enough times, and the baby goes, that's an apple. That's how we learn. The more training data the human brain has, then the better it is at predicting outcomes that the senses have not experienced before. So the really important thing is that if you teach a child to cross Oxford Circus, then they will be able to cross any road in the world, unless they go to IBC, of course. Because what we're giving them is generic instructions on how to cross a road. We don't take them to every single road in the world and say, this is how you cross this road, this is how you cross that road. Just say, here's a generic set of how you cross a road, and hopefully they learn enough to then be able to cross that road. So therefore the training is used to cross all roads. And this is what we're doing with machine learning. The more data we can throw at the system, the more sort of generalized the model can be, so the more things it can do with data it hasn't seen before, whether it's classification or prediction or whatever you've trained it to do. So this is a typical workflow of how we do machine learning. And this is supervised learning. So there are generally two types of learning, supervised and unsupervised. I predominantly work in supervised learning, which means we have to have a labeled data set. There is unsupervised learning, which I've not had much experience with, but instead of having a training set with labels, what we do with unsupervised learning is set a goal. And then you just say to the model, right, now you go and work out how to do the goal. So, annihilate the universe. Go think, that kind of thing. So with supervised learning, we have a training set with labels. So this is all my TCP data flows with the data packets that are either labeled as 1 for an elephant flow and 0 for a mice flow. We forward pass that through a neural network. I've got some diagrams of that in a sec. Compare the calculated value to the expected label value, so the output of the neural network compared to what it should be, and then update what we call the loss value, and then propagate that through the network to adjust the weights and biases within the network. So let me just, we'll come on to that in a sec. So ML is so powerful because the program and data analyst does not need prior knowledge of the problem they're trying to solve. That's incredibly important, because it means that as long as we've got a labeled data set, which has been labeled by experts, like the people in this room, for a specific application in broadcasting, we can give that then to a developer or data analyst who can take that data and they just treat it as data. They don't care it's video, it's a picture. I mean, they care it's video because the different models they apply. but they just treat it as data. And then they can build models that give you the outcome, and then they can supply you with a solution. So that's where we need the data set. And through a method of learning, the model is able to find patterns to help with classification and predictions. So classification is the stuff I'm doing, EF and MF detection and classification. Predictions is things like ChatGPT, where you say, write me a thesis to finish my PhD, and it will spit something out in 10 seconds. The only problem is the chances are your supervisor got there before you. So what is a neural network? This is a pictorial representation of what we call the neuron within machine learning. So we have multiple inputs, we sum them together, we have a bit of DC offset we call bias, we have an activation function, so this takes an analog value here and sort of makes it tend towards 1 or 0 or -1 depending on what we're doing, and then we have an output. So it's like we apply data to this network and it gives us, it fires a neuron. And that's why we sort of think in terms of the human brain, because that's where the similarity is. So we take multiples of those neurons and then cross-hatch them together to form a network. So each one of these is one of these, or one of these, or one of these. And the terminology we use is the input layer, which is where your raw data is coming in. Then we have the hidden layer, which is stuff going on inside. And then we have an output layer, which is giving you your response. And so when we talk about training a network, each one of these neurons has parameters associated with it, and they're sort of like multipliers and these DC offsets, weights and biases, as we call them. And by varying those weights and biases, we can generalize the model so it can respond to data it hasn't seen before and give you an output. And the way we look at that is through, or the way we train that is through a method of backwards propagation. So we pass the data through the network forward, we get our answer, compare with what it should be, find the difference, the loss value, then use that to then backwards propagate through the entire network through each of all of these, which then is used to update the weights and biases. And that's what takes the time when we're doing the learning. It's that massive calculation that's going backwards, because this is a very, this is so simple it's useless. It doesn't do anything. The neural networks I'm playing with have got, I think, 250,000 neurons. So if you can imagine backwards propagating through those is really difficult. And the mathematics behind this is really complex and really groovy. And if you ever did A-level maths and you're thinking, what point is the chain rule? Here's the answer. If you want me to come back one day and talk about that, I'm more than happy to do so. So what we have here is backwards propagation of gradient descent, or gradient descent, as also we're trying to achieve. So what we're trying to do is find these minimum loss values here. And this is where the calculus comes in, because we're differentiating the output with respect to the weights and biases so that we can then try and find our minima. If we do dx by dy equals 0, that's what we're trying to find here. Now when we're training, and again this is only a 3D model, the dimensions we're working with could be tens or hundreds, and it gets to the point after 3D that you can't actually pictorially represent it, so that's why we rely on linear algebra. And so, ideally we might want to be here, we might want the network to train to be here, but it gets stuck here. And so that's why we get training errors. And that's why I have to keep throwing lots of different data at it, because we want it to try and find this. But we can't see this. We just know it exists somewhere. We just know there's a solution, or we assume there's a solution. And that's why the data scientist comes in, because what they're trying to do is find the lowest value here so that they can get the best output. So these are some examples of ML models you'll hear. Recurrent neural networks used in sequence to prediction and speech data. CNNs, convolution neural networks, which are used a lot in video. If you know anybody who's doing ML in video, they'll be using CNNs and GANs, general adversarial networks. Video prediction for unsupervised stuff. This is really quite sexy. Long short-term memory. This is what I'm using within my models at the moment, and these are networks which have a certain amount of memory, because one of the problems, I did start using RNNs, but one of the problems they suffer from is something called gradient descent collapse, because the values just sort of tend to 0, which makes it useless, but these LSTMs fix that. And then there's transformers, which is the next big thing, and it's the thing I'll be working on next when I get this one working properly. So, how do machines learn? That's the answer. It's all about the data, right? You must get the data set right. But the other question is, who owns the data? And this is the really difficult bit, because in academia it's great because we have all these data sets that we can use because they're available for research. When you start building products, you have to find out who owns the data. And that can often be a very interesting question. And philosophically, that gets very deep very quickly.